So here we go. I'm going to clear this off, clear all the settings so you can see what's going on here. This is the end product. I'm going to reset everything. So the first place you'll be is actually at this window, and this is the Forces in Motion Lab for PhET activity. You're going to want to click on the top tab that says Force Graphs. It'll look like this. We're going to add, this is a force graph. We're going to add an acceleration graph, a velocity time graph, and a position time graph. And we're going to go through here and we'll make some changes. So this guy's going to push on this crate. I don't want him to push on the crate. Actually, the crate won't be selected at the beginning. It'll be a filing cabinet. So go ahead and make sure the small crate is selected. This information here says it's 100 kilograms, which gives us a force of gravity. Actually, the force of gravity would be 980 newtons, or its weight would be 980 newtons. 1 times 9.8 is, or 100 times 9.8 is 980 newtons. Here is our different types of friction. This is called kinetic friction. It's actually a letter mu. Mu sub k means kinetic friction. And this is the static friction. So this is the friction we get when it's moving, which is 30% of the weight. And this is the friction we get when it's not moving. It's standing still. It has more friction. This is always the case. There's more friction when an object is standing still, 50% of the weight, as there is when it's moving. It becomes less, because the fact that you're moving, you kind of like get up and out of the grooves which cause the friction. So I'm going to put here a vector force, which shows the sum. It'll look like this, and so you'll see some of the forces, and there's no sum of the forces here right now, so it's balanced. It's not accelerating. I'm going to move this back to a position of -8 meters. -8 meters, and it puts the back over here at the beginning. And you'll see that the friction right now is 93 newtons. I'm not sure why it says that right now. I'm going to click on friction. I'm going to click on sum. What I'm going to do right now is I'm going to get it. I'm going to get started with the recording of what's going on. So the first thing you're going to do is you're going to put the friction, or the force, the applied force of 490. And when you do that, you're going to see that this guy's pushing 490 newtons of force, and the friction is opposing that with also 490. Now I'm not sure why it's not showing that. Maybe when I push play, it will show that. So it's not going to move. I'm going to do this for 2 seconds, by the way. So you'll see this move to 2 seconds. Here's 2 seconds. So I'm going to say go, and I'm going to stop it manually. Ready, set, go, and stop. I overshot it a tiny bit. I can get closer than that. So here it is. I guess we needed to have it moving. So 490 newtons minus 490 newtons gives us a sum of forces of 0. So this is balanced, meaning that it's sitting there. An object at rest will stay at rest unless acted upon by an unbalanced force. And these are balanced. I'm going to zoom in a little bit here, and you can see that is the force applied minus the force of friction gives us a sum of 0. That means that the acceleration is 0, the velocity is 0, and a flat line means it's not moving. This is the position time graph. It's staying at -8 meters. What I want to do is I want to show you how it accelerated it. So at least 491 will get this to go. Just to make my, because that will be greater than the force of friction, which is 50% of the weight. That once again, that's a static friction. 50% of the weight is 490. I'm going to put it at 494, and there's a reason I'm going to do that. Is because I want to get nice even numbers. So 494 is above 490, and it will begin to accelerate. So for the next 2 seconds, I'm going to push play. I'm going to let it record for 2 seconds. I'm going to try to stop it as close as I can to 4 seconds here. Ready, set, go. And it begins to accelerate and stop. We'll overshot it a little bit still. So I'm going to increase this so I can see this a little better. So you can't really see it here. You only see it, only be able to see it there. It went from 490 newtons to 494. What happened here is the force of friction, which was a negative 490, dropped all the way down to a negative 294. The reason it did that is because 294 is 30% of 980. So the kinetic friction, or the friction where it's moving, is less. And so now my applied force is greater than my force of friction, and this means that I'm going to accelerate. The sum of my forces is to the right. If I zoom in here, you'll be able to see, yes, indeed, I am accelerating. So this shows that I am accelerating. If you wanted to know a value, the acceleration is 2 meters per second. It makes sense because I've got 200 newtons of sum of force, 200 newtons over 100 kilograms gives me an acceleration of 2 meters per second. And I've done this for 2 seconds, and I've gotten almost to 4 meters per second. If it was exactly 2 seconds, it'd be 4 meters. Okay, now what I'm going to do is I'm going to want to not go to a sprint. I want to keep going, but I want to go at the same speed. So in order to go at the same speed, I'm going to kick this down to 294. 294 changes this arrow to the same as this arrow. And so now my sum of forces is 0. That means that an object in motion will stay in motion at the same velocity as long as the forces are balanced. And so I'm going to do this now for 2 seconds. Ready, set, go, and stop. I'm going to increase this so you can see it. And you'll see that the velocity increased for 2 seconds, and then the next 2 seconds, it stayed the same velocity. An object in motion stays in motion at constant velocity if the forces are balanced. Come on in. So the force applied is less, it's equal to the force of friction, which means my sum of forces is actually 0. That gives me 0 acceleration. But since the object is already moving, it just continues at that speed. A straight line on the position time graph indicates constant velocity. This area before this indicates acceleration. So positive force, positive acceleration, increasing velocity, and a curve says I'm accelerating. 0 sum of the forces, 0 acceleration, means I'm staying the same velocity, and I have a straight line indicating that I'm going to constant velocity. Now I don't want to run into this wall, so now what I want to do is I want to stop pushing so hard. I won't stop pushing, but I want to stop pushing enough so it gets exact mirror image on this side. It looks exact same. And so I want to have the same numbers on this side, so I'm going to put 94 newtons here, and that will give me a total force of a sum of a negative 200, and that will slow me down to a stop. And so I'm pushing slightly, and the friction is going to take over. I'm going to slow down until I stop. And so for the next 2 seconds, 1001, 1002, and there we go. And so I stopped pushing so hard, the friction was still there, so my force was negative. That gave me a negative acceleration, and that slowed me down from 4 meters per second down to 0 meters per second. And my velocity curve, my position time curve is curving back to no motion. So there you have it. That's what we're going to do in our lab. I'm going to play it back for you so you can see it. But that's what we're going to do in our lab. You can try to do the exact same thing. And then quiz 2.3 is pertaining to this activity. So first section, push play. That section is called static equilibrium. The forces are balanced. No acceleration, no velocity, no movement. Then I'm going to go into acceleration, where now my forces are larger than my force of friction. And so I have a positive force, which is the green here. Oh, by the way, the applied force is this amber color, and the friction is this red color. And the sum of the forces is the green color, which is 200. And so this positive force of 200 gives me acceleration of 2. And this shows my velocity increasing, and this curve also shows my velocity increasing. I'm going to push like that until the middle section. In the middle section, I'm going to ease off on the force so that I don't have to run across the floor. My force is now 0, and my acceleration is 0. But since I was already moving and an object of motion stays in motion, means my velocity stays the same. This straight line section means the velocity stays the same. I continue to the end, and I begin to slow down to a stop. And so in this section, I've slowed down. My forces are negative. My acceleration is negative. My velocity goes down to 0. My curve curves down to where it's flat. That means I'm not moving. So let's see that one more time in fast motion. Static equilibrium, acceleration, dynamic equilibrium, deceleration, and then finally stop. Go ahead and try to do this on your own in the PhET activity online, and then go ahead and see if you can do this for the quiz. The quiz has everything to do with this activity we just did. Have fun.